Okay, so you've already have the link, no, for the derivation of undamped force vibration. Okay, just a quick recap, no, of that one. And so yeah, so this is undamped force vibration, and this is our applied force. Now remember, our equation of motion is this one for undamped force vibration. The applied force to our SDOF is a harmonic force. So nandito yung ano na yan, P sine omega bar T. Okay, the omega bar stands for the frequency ng load, no? Kumbaga kung ito yung structure mo, mayroon kang applied force, no? May frequency yan. Okay? And then also, your structure, this SDOF, also has frequency. We call that omega. Okay? Now, you'll notice naka-subscript siya na P because we are solving for the particular solution. The homogeneous solution, we already know that. No? Yung last time dinerive natin. No? According to differential equation, the solution of a non-homogeneous differential equation, by the way, this is non-homogeneous differential equation. Ang solution daw niyan is the combination of the homogeneous solution plus the particular solution. That's why we're now solving for the particular solution, which is this one. And the assumed particular solution is u sub p equal to g1 sine omega bar t plus g2 cosine omega bar t. And by the way, no, for section F, no, you will be having an assignment that will be submitted next week, no, because next week is exam week, quiz 1. Okay, so and your assignment will consist of detailed derivation ng mga previous na dinerive natin. Kasi may mga derivation ako na hindi ko na pinakita in detail, no, because like I said, some of them are basic algebra lang, no. So I want you to perform that, no, on your own. Okay? Sige. So back here, so u sub p is equal to g1 sine omega bar t plus g2 cosine omega bar t. Find the first derivative and the second derivative. Once you know the second derivative, substitute do sa ating equation and expand and then find the common terms. Okay? And then algebra, you will get this. Okay? Now, when you have this kind of situation or equation na merong sign sa right side tapos at the same time may sign din sa left side, etong term na to will be zero. No? So hindi sila mag-appear at the same time, no? Na may sign dito tapos cosine tong kabila tapos sign naman sa right side. Therefore, this is yan, itong term na to is 0, so equate natin to 0, therefore G2 is equal to 0. Then ito naman, simplify this, you will get G1 equals to this. Okay, and then algebra, which is actually part of your assignment, you will obtain this. Okay? And that's your G1, plug in mo dun sa assumed solution. Remember, G2 is equal to 0. So, ito na yung lalabas na particular solution natin. Okay? Then, combine that with the homogeneous solution. Yung particular solution natin. Yan. Okay, this is the particular solution here. Combined with the homogeneous solution. Ito na siya. Because C2 is equal to 0. Remember? No, that's last week. lecture natin. And so find the first derivative, or sorry, set t equals 0. Okay, what's that? Yan. So, yan. Find the first derivative nito, of this equation. Okay. By the way, beta is, yun nga, the frequency ratio, omega bar over omega. Then, once you find the first derivative, ito siya, then, substitute t equals 0. Yan. So, lahat ng mga may t going 0. So, you will have cosine omega times 0, which therefore cosine 0. And cosine 0 is basically 1. No? So, simplify, maging ganito. Then, therefore, C1 is equal to this. Okay? And then, plug in C1 to the solution, then you will have that. So this is now your our solution for, so isulat ko ha, for undamped force vibration. So U of t is equal to P naught over K 1 minus beta square sine omega bar t minus beta sine omega t. Okay? Yeah, so yan yung ating solution for the undamped force vibration. Okay. Then also, next, another assignment, no? If beta is equal to 1, of course, that is resonance. No? Kasi nag-equal yung frequency ng, force dun sa frequency ng structure. No? So that's resonance. And you will derive this. Okay? So remember, if beta is equal to 1, dito tayo. If beta is equal to 1, this is 1, diba? 1 minus 1. So therefore, itong denominator mo ay 0. So this term divided by 0 is, alam natin, undefined yun, no? So, how do you solve that? So calculus, no? You will be using what we call Hospital's rule. Pero ito yung spelling niya, alam ko no? Hospital's rule, no? In order to solve this equation, wherein beta is equal to 1. So you will derive this. Okay? And then the graph of the amplitude of the displacement will be something like this if you have a resonance. Okay? Then for the solution of damped force vibration, ito naman yung equation. So siyempre mas mahaba, no? Because here meron ka ng damping ratio na involved. Okay? But I want to emphasize here that this term is the steady state response, while this term is the transient response. From the word transient, no? Minsan lang mag-appear, diba? Pag makikitulog ka, no? Or magre-rent ka ng house for a night, no? So, and I have a transient uh, uh, transient rate, no? May ganang transient rental, di ba? For may kitulog, no? Yan. So, because hindi siya mag-a-appear the whole duration of the response, no? And ito yung plot na yun. Okay? Whereas the steady state response will appear the whole duration. Okay? And as you notice, you have your P over K. And remember what is P over K? That is your static displacement. Well, from the formula P is equal to KU. Then transpose, you'll get this. Okay? So meaning, no, the meaning, no, the particular solution, no, that we solved earlier, no, is actually the steady state response. So ito na yung physical meaning ng differential equation, no? Yan yung physical meaning, the steady state response of your structure. While yung homogeneous solution, siya yung transient response. Yan yung physical meaning niya. Okay? Yeah. So, we're going to solve a problem, no? Applying this formula. Ito siya. Yeah. So let's say we have a single degree of freedom problem idealized as SDOF itong tank na to, water tank. Okay? So meron kang applied force na 100 kips, no? Syempre may frequency siya, no? Sin omega bar t, so it's actually a harmonic force, no? Then the frequency is 30 radian per seconds. So let's say what's the response, no? Let's solve the response at 0.1. The displacement at 0.1 seconds. Sige, so let's rewrite. No? So I'll write down P naught over K. So my P naught is 100 kips divided by the stiffness, 100 kips per inch. Okay. Then 1 minus beta square, unknown pa siya. Then sine omega bar. So what's our omega bar? 30 radian per seconds. 30 times, of course, the time, 0.1 minus beta sine omega. So unknown pa si omega, our natural frequency. Okay? Yan. So as you see, cancel tong kips, no? Ang matitira is inch, no? So 1 minus beta square Okay. So, right now, beta, unknown pa natin, no? And also, the natural frequency. So, let's solve first beta. However, no, beta is basically omega bar over omega. So, yun nga, hindi pa natin alam si omega. So, what's the formula for omega? It's square root of k over m. So, what's our k? 100 kips per inch over mass. Ano yung mass natin? Our mass is W over G. Ang ating weight is 38.6 kips. So 38.6 kips divided by G. Remember, this is in English units. No? Our G is 32.2 feet per second square multiplied by I want the since naka-ano tayo, naka-inches, no? And then let's try to convert everything in terms of pound, inch, yun, pound, inch, no? So this will be 12 inch per 1 foot. Cancel to. Then, ito naman, convert natin sa pound, no? So, 1,000 pound is 1 kip. Yeah. So, what's the result? Wala. So 38.6 times 1,000 divide 32.2 divide 12. 99.896 no, pound inch per second square. So yun yung mass. So, yun din dito times ano nga to? Ganun din, multiply sa 1,000 pound per kips. Cancel to. Then the mass is 99.896 pound inch per second square. Okay. So cancel si pound here. No? Cancel si inch here. So matitira, second square. Tapos square root of second square, seconds. Kaya radian per seconds. Radian is unitless yan. No? 100 times 1,000, 99.896 square root of the answer. So I got 31.639. Okay? So yan yung omega. And then ito yung mass. So we can now solve for beta. Omega bar is 30 divided by 31.639. So 30 divided by the answer. I'm getting 0.9482. Okay? So if you notice, almost 1 din siya. No? So malapit na sa resonance. Okay? Now, sige. So plugging in this term So, ito na siya, 0.9482, omega as 31.639. Okay. Yan. Then solving that, so beta is 0.9482. Okay. So what do you get for the displacement at 0.1? So you will get, according here, solve din dito, so you should get this. 0.1 is 1.6. Kung may discrepancy, konti, no? This, nandun siya sa range na yun dapat. So, 1.6 inch. And quickly, no, if, let's try, I hope, no, kasi kung face-to-face to, no, papasolve ko sa inyo to, at 0.3, you will get, supposedly, to 4.674. Okay? So, as you notice, no? Palaki ng palaki. No? 1.6 inch at 0.3 seconds naging 4.674. So, pag plinat mo yan, you will get something like this. Ganyan. So, nag-modify habang tumatagal yung displacement. So, ito si 1.6. Then, ito naman si 4.674. Okay? Because of the beta, no, na almost resonance. Okay? So, which proves that, no? By the way, no, what's the static displacement? Basically, the static displacement is just U static P over K, di ba? Ito na yun, solve na natin yun. 100 kips divided by 100 kips per inch. So, that's basically 1 inch. 1 inch lang yung ano, yung 100 kips, if it's acting alone, no? I mean, statically, 1 inch lang yung lateral displacement. However, dahil may frequency siya, or may ratio, yeah, may frequency siya, that's almost in resonance dun sa structure, nag-magnify yung displacement. Okay? Well, to be exact, ito yung kanyang plot. Ay, sorry. Yan. So, in Excel ko na yan. So, let's say dito, palitan ko yung omega bar as 30. Ito siya. Okay? Nag-magnify. Okay? Ang ating nakukompute na ano is just 1 inch. Pero umabot ng ano, makapapansin nyo, no? Almost 20 inch pa. Okay? So, meron na rin kayong spreadsheet niyan, no? Binigay ko na yan doon sa last problem, kasama itong Excel sheet na to. Okay? So, that's just an application for undamped force vibration. Now, again, that's utilizing this equation. Now, what if, not resonance? So, assume tayo. Palitin natin. Sabihin natin 10. Tingnan natin yung plot. Yan. So, nakikita nyo, hindi siya, syempre, not resonance, no? So, cyclic yung, ano niya, yung motion niya, no? Halos iisa ng displacement. Okay? Okay. How about 2? Siya. Okay. Say 6. Ayan. Okay. Halos, yung amplitude niya, 1.12. Ito is 1.18. No? So, yung amplification niya is only what? No? 18%. No? Unlike yung kanina, more than ano pa no? More than 20 pa, no? Or more than 10 yung amplification because almost resonant siya. Ito, ang liit lang kasi ng omega bar, no? Yung beta mo dyan is 6 divided by 31, no? Ang liit lang, no? Point something lang. Okay? Now, a quick check for the damp force vibration naman. Ang gusto ko naman ipakita sa damp force vibration is oops. Yan. Ito. Yan. So, for the damp force vibration, ito siya. Ito yung equation niya, no? And as you notice, nandun pa rin nga yung static displacement. Now, let's deal with this, no? Yung ating dynamic amplification factor. So, i-rewrite ko lang. So, 1 over 1 minus, actually beta yan in our terminology. So, square plus 2 beta damping ratio square square root. So assuming I dito. Yan. So let's say my damping ratio is 0.25. Then my beta is equal to 1. What is my D? Yan yung dynamic amplification factor or magnification factor for damp force vibration. If you solve that, you will get D as equal to 2. So, kagaya nito, no? So, my beta is 1. Tapos, my damping ratio is 0.25. Yan. Project ko to. Hanggang doon sa 0.25, you will notice, you will get a dynamic magnification factor of 2. Okay? So, meaning, by playing with this formula, no, by varying the damping ratio, varying the beta or the frequency ratio, you will achieve this graph. And so even mechanical engineers, no, ginagamit din yan. Lalo na sa case nila, no, for example, may generator, no, nakapatong sa beam or slab, no. Siyempre, yung generator na yan, meron niyang vibration, no. So yung vibration na yan, may omega bar yun. And then yung slab mo, or beam, meron niyang omega, natural frequency. So by knowing the frequency ratio, no, between the applied generator, harmonic force, and its and yung support, yung slab or yung beam having natural frequency, malalaman mo yung dynamic magnification factor for a certain damping ratio. Okay? So yan yung mag-generate. So that's for the damp force vibration. Saka na yung mga specific example. Because aside from this, gusto ko ding na tayo sa response spectra. Because gagawin niyo yun sa plates ninyo. Ayan. By the way, no, before I proceed with the response spectra, sulat natin dito yung ating equation of motion. Diba? It's mu double dot plus cu dot plus ku equals force, no? With respect to time. Of course, under earthquake, so basically this is SDOF under earthquake ground motion. And the earthquake ground motion, this is basically negative m times g double dot. Okay. So if we divide our equation by m, you will get u double dot plus c over m u dot plus k over m u is equal to negative g double dot. Okay. Now, remember that the formula for damping ratio is this. So, yun yung dinerive natin nakaraan. I mean, yung in-establish natin equation. So, sa finding the C over M, you will get 2 Greek C omega. Okay? So, plug in natin dyan. Plus 2 Greek C omega plus. How about K over M? Remember, omega is equal to K over M. No? So, therefore, omega square is equal to K over M. Right? So, therefore, this is omega square U is equal to negative G double dot over T. So, this is now our derived equation for SDOF under earthquake ground motion. So, which basically means, no, na yung response, no, ng ating single degree of freedom problem, na let's say, sinubject mo siya sa earthquake, yung response niyan, no, pag nagkaroon ng earthquake, is dependent on the two major factors, the damping ratio and the frequency. So, kung alam mo yung damping ratio, which sabi ko nga, generally taken as constant, no, for concrete, 0.05, and if you know the omega, which is a function of K and M, no, makukuha mo na yung response ng building mo. Okay? Under earthquake ground motion. Yan. However, no? However, this ground motion is non-linear. Hindi yan harmonic force, hindi yan sine omega bar t, hindi yan cosine omega bar t. Diba? It's non-linear. So the only way to solve this is numerical methods. So you need to have to know a numerical methods approach. And kaya meron kayong numerical methods last year, or nung third year. Yeah. So ito nga, in our case, we will use central difference method. Okay? So ito yung formula niya. So for example, pakita ko lang. I-post nyo na lang yung video, no, kung para sa mga formula gusto nyo makita in detail or matagal, no? So, for example, you have a displacement versus time curve, no? So, alam naman natin, velocity is equal to displacement over time. So, we need to find the displacement or basically it's dx over dt. Yan. So, rise over run. So, what's the rise? So, the difference ng displacement. So, ui plus 1 minus ui minus 1 divided by the run, delta t. Ang run mo is ito, which is basically twice the delta t. No, ito kasi yung u sub I, ito yung ui plus 1. So, and then that's the delta t, so twice of that. Ito siya. Okay, now for the acceleration, no? Alam naman natin, acceleration is dv dt. Diba? So, ang rise mo naman, yung difference ng velocity with respect to time naman. Okay, so, kailangan mo makuha yung velocity. So, u double dot, you know, ui, no, double dot. So, the central difference, no, pinapagitnaan natin. Like ito, sa velocity, pinagitnaan natin si I, which is ito yung dalawang pumagitna sa kanya. Okay? So sa velocity, ang papagitna sa I, pwede rin yung I plus 1/2 and I minus 1/2. Ito yun. Yung data dyan. Yung velocity dyan. Okay, so we need to find the velocity, the formula of velocity at I plus 1/2 and the formula of velocity at I minus 1/2. And by using the central difference method, ito yung makukuha nating formula. Okay, and then substituting dito sa formula ng acceleration, algebra, simplify, no, you will get this. Okay? So ginawan ko na yan ng ano, no, ng spreadsheet, no, which I will give you. So para lang magka-idea kayo. And also may mga video na rin ako dun sa about dun sa spreadsheet. No? So, ito yung algorithm niya. Yan, yung algorithm. Okay. And then, ito yung pinaka-spreadsheet niya. So, bigyan ko din kayo ng link about yung detail ko din paano gamitin yung spreadsheet. Anyway, so sabi nga natin, no? Basically, what we need is the omega or the period and the damping ratio. Kaya siya lang yung input. Yan, siya lang yung input. Okay. Now, so let's check 0.5 second structure. Yan. By the way, this is yung El Centro ground motion. Ito yung pinag-aaralan nating El Centro ground motion. Kumbaga, let's assume an earthquake. No? Siyempre, sa earthquake engineering book, ang pinakasikat na ground motion is the El Centro ground motion. So, ito siya. Ito yung, roughly, ito yung kanyang tsura. Yeah. And as you notice, no, nasan yung kanyang PGA? And basically, ito di ba? No? And if you click on that, or sorry, browse mo dyan sa location na yan, the maximum or the PGA is at 2.02 seconds. So, let's say ito, 2. Ayaw mo na. Lobat na yun ako. So, anyway, 2.02 seconds. Tapos, 0.32 G. 2.02 seconds. Nangyari yung PGA niya, tapos 0.32 G. Yeah. Take note, no? Sa NSCP natin, no, we are under zone 4, which corresponds to 0.4 G. Sabihin nun, no, parang sinasabi sa code na under 0.4 G, dapat hindi mag-collapse yung building mo. May damage, yes, pero never collapse. So itong pinag-aaralan natin is 0.32 G lang, no? Kasi ang code nga natin requires 0.4 G. Okay? Yeah. Okay. So next is, sulat ko lang ulit, sulat to second, 0.32 G. So let's study the response of the 5-story building. Kasi nga, 0.5 seconds. Sulat ko dito. So, 0.5 seconds. So, to exaggerate, no? Lagay ko 5-story. And 5-story. And then, utilizing this spreadsheet, no? And, so, ito yung acceleration. Yan. Downloadable din naman sa internet yan. Yung mga text file niyan. Paste ko lang dyan. Ang duration kasi yan, mga 30 seconds. No? Tapos, yan. Nakikita nyo naman yung formula, no? So, mass times acceleration, multiply yung mass, acceleration, may column pala dito. Yan. By the way, yung delta t nito is 0.02 pala. 0.0. Anyway, so, then ito na yung corresponding displacement. And then ito na yung plot. Yeah, response of 0.5 second structure. So, yan na yung plot ng response ng 5-story building. Diba? Because 0.5 seconds, roughly, 5-story building. No? 5-story building. So, obviously, saan yung maximum displacement? Ito siya. Yan. 2.32 and then 2.71 inch. So, sulat natin, no? So, ang kanyang maximum displacement, 2.32 seconds, 2.71 inch. Yan. So, proceed naman tayo sa 1-second structure or 10-story. No? 10-story. So, 10-story. Click ko to. Yan, kita nyo, naka 1 second. Tapos, still, damping ratio is 0.02. And ito naman yung kanyang plot. And ang kanyang max is 4.8 seconds. No? 4.8 seconds. Tapos, 6 inches. 6 inches. Okay? Siguro last for the purpose of 2 seconds. What is 2-second structure? A 2-second structure is 20-story. Yan, yung mga nagko-condo dyan, no? More than 20-story pa nga, no? 20-story. So, ito yung plot niya. Ano ba? Parang ito, no? 11.18, 7.48 inch. 11.18 seconds, 7.48 inch. So I'd like you to quickly check the difference. So naalala nyo, no, yung 5-story building, no, yung peak displacement niya happens at 2.32 seconds. Pero 2.71 inch. Okay? While yung 10-story, 6 inch. Siyempre, mas mataas na building, mas malaking displacement. Pero yung peak displacement niya, nangyari at a later time. No? 4.8 seconds. While yung 20-story building, no, yung tallest among the three, is siyempre, mas malaki pa rin yung displacement, 7.48 inch. Then, nangyari yung peak displacement niya at a later time also, 11.18. And so, if we are going to plot that, yung trend na yan, so, I'll plot that here, something like that, ang ganyan, no? So, yan. So, nandito si 2.71 inch. So, sabihin natin, this is 0.1, tapos 0.5, tapos 1 second, 2 seconds. No? Then yung value ay 2.71, 6 inch, 7.48. Okay? So that is what we call the displacement response spectra. The displacement response spectra. So which shows that as your building goes taller, no, your your displacement gets higher. Yan. Okay? So yung next naman niya, next plot naman niya is the velocity response spectra. Actually, ito na isama nila. Something like that. So if I were to copy that, just being somewhere, something like here. Oops, not. Oops. Ganyan, no? Then yung acceleration response spectra, so ganito, masyadong dikit eh. So, ganyan. Yan. Okay? Kasi ito yung 0.5. So, kung ipoproject ko to, ito. Yan. Kung ipoproject ko. Tama? And if I will to write that, ito abot ng 1.1 G. So this is 0.32 G. Okay. And by the way, no? Yan. So, to compute for the velocity response spectra, madali lang, no? Basically, multiply mo lang yung frequency sa displacement. Since may data ka na ng displacement, multiply mo lang sa corresponding frequency. And for the acceleration, omega square d. Ganun lang. Okay? So now, so what do you notice, no? You notice, no? So yung 5-story building, no? Of course, 2.71. Pero tingnan niyo yung acceleration response spectra. Siya yung pinakamataas. Ibig sabihin, no? Meron kang let's say ito yung structure mo, no? Yan. So ito yung structure mo. So dito sa ilalim, may 0.32 G, no? Pero mabilis lang yan. So syempre, mabagal muna, biglang mabilis, 0.32 G. 0.32 G, tapos, syempre, nag-subside, no? Pero, sometime, no? Biglang nag-accelerate dito taas mo, no? Kumbaga, ito, 0.32 G at 2.02 seconds, diba? Then, ito naman, nag-accelerate ng 1.1 G. Yung peak niya, no? Ganon. Yung peak naman niya. So, there's a tendency that sa ilalim, 0.32 G, pero sa taas, 1.1 G. So, ganun kabilis. No? Yung, let's say, what is 0.5 seconds? 5-story. So, parang ito, Koi building. No? 5-story. No? Nagkaroon ng 0.32 G na earthquake, yung mararamdaman sa taas, sa 5th floor, is 1.1 G. So, ganun kalakas yung spectral acceleration na tinatawag. So, ito yun. That's the spectral acceleration. Yung nararamdaman sa top. Okay, the maximum acceleration. Okay? However, So, on the other hand, no, yung 1 second building or 10-story, no, pagdating nyo, yung acceleration bumaba. Nasa 0. Ano nga lang yan, no? What is that? 0.6. Diba? 0.6 G lang. No? Meron kang, so sa 10-story, no? 0.32 G, pero yung naramdaman sa top, 0.6 G. Mas malakas pa rin. No? May tendency mas malakas pa rin. 0.6 G. Okay. And again, for the 20-story building naman, ang naramdaman lang niya is 0.2 G. Can you imagine that, no? 0.2 G. Sa 20-story, 0.32 G sa ilalim, pero dahil flexible na siya, ang bagal na niya. Ang mabilis sa ilalim, pero sa top, 0.2 G lang. So, as you see, no, habang tumataas yung building, ganun yung nangyayari. No? Na sobrang flexible niya. Ito, ang bilis dito, no? Ang bilis ng shaking dito, pero yung shaking dito, mabagal. Ganun yung nangyayari. Okay? So, that's the general trend. Okay. Now, I want you to now turn the attention to NSCP. That's why we're studying response spectra, because it's indicated in our code, in our NSCP. So meaning, pagka-graduate nyo, naging engineer na kayo, pipirma kayo ng structure, pipirma kayo ng blueprint, pipirma kayo ng structural permit, you are, parang implicitly, no, ito ang sinusunod mo, response vector. Okay? Which means, no, there's a mathematics behind this. No? We were able to derive this by numerically solving the equation of motion na ito. Using basically central difference method, if you prefer. No, kasi pwede ding Newmark's data, mga ganun. Okay, so now you know that this curve has mathematics, no? Derived mathematically. This has from a differential equation of motion. Okay? Sige. So for example, no, let's try to solve that. So isusulat ko, no? So yan. So ito daw ay CA. Then ito naman ay 2.5 CA. So ito naman yung ating T sub S. Ito naman yung ating T sub 0. Then yung formula ng T sub S is CV over 2.5 CA. And then, yun. T sub 0 is equal to 0.2 T sub S. Again. And also, we'll be give you this spreadsheet also para may guide kayo, no? Na using that formula, no? Will show that the response spectra, NSCP, as per NSCP, is basically dependent on the three parameters. Nabilang ko. So soil type. Ay, hindi niyo pala kita. Soil type, kung saan ano yung structure mo. And then, of course, yung zone 4. So, SD tayo, for example. Zone 4, what else? And the distance to the fault line. So, let's say your project is 10 kilometers. Distance, 10 kilometers. Okay? So, with that data, no, ayan, soil type SD, zone 4 corresponds to 0.4, source type A with a distance of 10 kilometers. This is our NANV and CACV. So, tingnan natin. So, my NANV is equal to 1, 1.2, then my CACV is equal to 0.44, 0.768. Okay, sige. So, let's try to compute. Yan. So, tayo. So, according yan yung ating automatic, this is CA no? So, ito. Yan. So, this value here is our CA, which is 0.44. Okay? Then ito, 2.5 CA. So, 2.5 times 0.44 is 1.1. So, this is 1.1. Which, what do you notice? The same lang sa nakuha natin. No? Under el centro ground motion. So, meaning, yung 0.32G, 0.4G, there's a chance, no, or there's a high possibility na yung spectral acceleration mag-the-same. No? Yan, kuha natin, almost 1.1. Okay? So, yung response spectra natin came up with the same, no? 1.9. Okay? So, parang sinasabi dito, no? Kung ang project mo is nasa soil type SD, stiff soil profile, alam niyo na yung ibig sabihin ng stiff soil profile, na-discuss ko na yan, even sa PCS1. Tapos, nasa zone 4, which generally, 90% ng Philippines, halos zone 4. Tapos, ang distance mo sa fault line, 10 kilometers. Parang ito, Manila, no? West Valley Fault, 10 kilometers away from Manila, Intramuros, for example. Yan yung corresponding response spectra ng site, ng project. Okay? So, how about T sub S? So, T sub S is equal to CCV 0.768 divided by 1.1. So, get 0.7. Yan. So, meaning ito ay 0.7 seconds. While T sub 0 ay 0.2 times 0.7, 0.14. Yan. So, may ano ka na, no? May coordinates ka na ng response spectra. Okay? So, naalala nyo, no? Meron tayong provision na kapag ang period ng structure mo ay 0.7, no? Hindi mo na i-include yung F sub T. So parang ganito yung explanation. No? Because you will notice, no? Ito yung delineation. Ito yung 0.7. Because as your building period goes higher, meaning from 0.7 upwards, no? Pumapasok ka na sa mid-rise to high-rise. Dito ko na napupunta sa region na yan. Okay? No? Yan. Okay, next. So siguro, iyan natin, fill out natin yung other details. For example, so assume tayo for 1 second and 2 seconds. Ano yung value ng mga yun? Ng mga nandito. So basically, the formula is, according to NSCP, CV over T. So CV over T. The formula, CV over T. For 1 second, CV is 0.768. No? So basically, this is 0.768. Ito ay 0.768 divided by 2. So that is 0. Wait lang. Tama. 0.384. Okay? So ito yung ating design response spectra. So according to our spreadsheet, ito siya. 2 seconds. Tama. 0.349. Okay. So ang nakuha natin, ito. So check natin. Yan. So 1.1. Yes, correct. T sub naught 0.14, correct? Tapos 1.1, 1 sec, ano yan? Pwede, 2.2 for example, 0.349 tayo. Yeah, 3.384 kasi 2 seconds. So pag in-interpolate mo, you will get the same. Okay? So yan yung ano niya, yung detailed coordinates. So, ito yung mga major portion response spectra. Okay, so that's how you create the design response spectra. And again, no? And again, so that is very similar to our derived response spectra, solved numerically. in an actual earthquake. Okay? But take note, no? This one is design, meaning may conservative approach na si Cogen. Okay? Whereas ito, actual response spectra. Because the response spectra, no, for a specific earthquake, iba-iba. No? Iba-ibang response spectra kada earthquake. Like ito, response spectra to ng El Centro na 0.32 G. Like for example, Abra earthquake. Ang PGA ng Abra earthquake ay only 0.2 G. 0.2 G lang. So meaning, ang response spectra ng Abra earthquake will be somewhere like here, siguro, ganyan, something like that. I don't know. Pero definitely 1.1 G, hindi siya aabot. Okay? So, kumbaga, kung ipa-plot ko siya dito, siguro mga ganyan lang siya. Ayan. No? There's also a concept, no, why this topic is important. For example, no, nagkaroon ng Bohol earthquake. No? During that time, I think 2013, no, uncharted fault yung sa Bohol earthquake. So sabi ng mga ng ibang professional, change the code. Hindi kasi siya nakasakop sa NSCP. Wala sa mapa ng pivots. Right? However, if you did a response spectra of that, ganyan lang siya aabot. Meaning, ito yung design response spectra natin as per code, no? Meaning, yan yung dapat mong sundin as engineer when you're designing your building. Then, an earthquake happens, although uncharted siya, hindi pa na-detect sa mapa, pero ito lang yung kanyang response spectra. Right? So that means, by following the code, na-envelope ng NSCP yung response spectra nung earthquake na yon, kahit hindi siya nakamapa, no? Yung fault line. See? So that's the beauty of the code, no? Kasi syempre, it's a code, no? There's a conservative approach, no? Kailangan masigurado natin na kahit may uncharted, no? As long as this response spectra, design response spectra is not exceeded, supposedly your structure should not collapse. Okay, so that's another purpose of generating a response spectra for each earthquake. And then because you will compare that with the response spectra dictated sa code. Okay, kaya we have what we call the design response spectra. Kasi ito yung sinusundan natin response spectra. Okay, again, the response spectra generated, the design is dependent on different factors. Siyempre, iba-iba tayo, no? Depende sa soil, sa zone, and sa distance. Okay. Quickly, I'll show you what if, no? So, nakita natin, no? 1.1 G, no? What if ang project mo nasa bedrock. So yan, SA. Diba? Yan yung hard rock, no? Tingnan nyo yung response spectra. Di ba? Bumaba. Kanina from 1.1, naging 0.8. Okay? Because, remember, earthquake happens sa bedrock. Di ba? And generally, no, above the bedrock is a soft soil. Andun yung SD. Ito, sabi natin, SA yan. So, kung nangyaring earthquake dyan, pagdating sa soft layer, ma-amplify siya. Kaya lumalaki yung spectral acceleration. Kasi na-amplify siya sa soft soil. Okay? So, that's it. And lastly, no? Dito, no? So, unfortunately, sa Turkey earthquake, no? Let's say, in the context of design, yung nangyaring PGA sa Turkey, umabot ng 0.7. Taas, no? 0.7. Sabi nga natin, no? Our PGA, no, as per NSCP is 0.4. So, what if, no? What if yung response spectra sa code ng Turkey is not that high? So, something like this. Ito. Nangyari yung PGA na 0.7. And you can now imagine, no, if PGA is 0.7, syempre magmo-move to, no? So the response spectra will shoot up somewhere there. So, hindi na envelope ng code. Tapos nag-collapse. So, in the context of design, no, pwedeng sabihin ng designer, wala eh. Hindi yan na-anticipate ng code. No? Hindi, what they call this, hindi covered ng code. So, in the context of design, safe si designer. No? Kasi na-exceed ng Turkey earthquake yung design response spectra. So, may lusot, no? Kaya nag-collapse. No? But in the context of construction, no? Like for example, no? They observe maraming flat slab, no? Tapos hindi maganda yung detailing ng joint. And that's another story. No? There's another story. Okay? So, construction is a different issue. Okay. Ayan. So, that's it. So, yun yung ano, no? Yun yung, kaya yung response spectra kasi parang ano siya, no? It's a common language sa mga codes regarding sa earthquake, no? May response spectra si New Zealand, for example. May response spectra si Japan, no? So, pag nagkakaroon ng earthquake, you will notice response spectra ang nilalabas ng mga seismologists, no? Or even structural engineers to show that a certain earthquake was able to either exceed or not exceed the design response spectra imposed in the country. Okay? It's a way of knowing, no? Kung yung earthquake na yon will cause damage. Okay? Sige. So that's it. So by the way, no, this is not part of the exam 1 pa, no? So pinilit ko lang i-discuss para sa plates ninyo. No, may idea na kayo paano gagawin. Okay, so sige, I'll just give you this spreadsheet to aid you in creating the response spectrum ng project nyo, ng plates ninyo, and also the recordings, no, for your reference.